Let's see. Okay, so some administration. Trivia. The regrade requests. Regrade requests should be available for the exam. The midterm are available. You should check with me before. Submit a regrade, or check with any GSI. Check with me or any GSI before you submit a regrade request. So you can do that by just talking to me after section. You can check with me after this section. I'll be on for a little bit. You can private message me if you'd like, or we can just talk freely, or you can email me, or if there's more in depth, then you can, maybe we can set up a separate Zoom meeting or something. But in either case, you'll email me any logistics. What else? There's a quiz today. Why is this not? Quiz today. I think it's 24 hours. 24 hours. Are there specific times when you would use truncated versus full SVD? Good question. And for the true false in the quiz, do we need to justify? I don't know. Does it say? If it doesn't say you need to justify, then you can assume you don't for true false. In which case it'll probably be worth like 1 point. But you know, it doesn't hurt you to justify. We won't take points off if you justify. Well, actually that might be false. If you justify incorrectly, like very incorrectly, maybe we take points off. But usually it doesn't hurt you to explain your reasoning. Although if it doesn't say it's required, then you could probably assume it's for true false, it's not required. For short answers and so forth, it's always required you show your work and justify. That's a given. For true false, it's usually just either true or false, unless we tell you. Okay, another question. Are there specific times when you use truncated versus full SVD? So yeah, this is a question like on last section as well. And it kind of just depends what you're using it for. In practice, I'd say you usually use truncated SVD. Because, I mean, the purpose of SVD is kind of to get at the singular values and the singular vectors. One of the nice things about SVD is that you have maybe a bunch of big data or some things, or some, yeah, just a lot of data or a lot of big data. And it's hard to deal with. It's hard to visualize. It's hard to use. It takes up a lot of room. And so you want to truncate it to like a smaller subspace. Or you kind of want to store like essential information. And SVD is kind of telling you what essential information to store. So typically in practice, you use truncated SVD. But for the purpose of this class, since we're not doing any actual applications, you know, just use it whenever we tell you to use truncated or full. Let's see. Yeah, are there any? So let's see. I'll say there's not much planned for today, to be honest. We kind of talked, I mean, the lecture talked about SVD a little yesterday, I believe. We've done a few things with that. I mean, we can do another SVD example, and then we can kind of start talking about differential equations a little. But I think this section would be a little short, and then I'll leave it open afterwards for any questions on the exam. in full SVD is the same size as A. Yeah, that's correct. Yes. So by the way, that E is called sigma, the Greek letter. So the question is, in full SVD, no, that's fine. Full SVD, this is U sigma V transpose. This and this are the same dimension. So when you do sigma transpose, this is like, let's say A is like some big matrix like this. You're still going to get a big diagonal matrix. Let's say this is sigma 1 through sigma r, and then the rest are 0. But then at some point, you're going to get zeros afterwards. Right. And at some point, these all going to be zeros. And if you look at sigma transpose sigma, this will be a smaller matrix that has that'll have not as many zeros, or no zeros, if any. So this is what happened like some time ago, where we found some 0 eigenvalues for A transpose, but then no 0 eigenvalues for A transpose A. So it'll still be diagonal, but some of them will be zeros for the singular values. For the truncated, you have to choose what K is. What is K? Is K, is K the same as R that I've written here? For the truncated, yeah, so no, in that case, then no, right? So R is kind of given, is this R, or in your case, K, is the number of singular values of A, or non-zero singular values, I guess, which is just given to you. Or not given to you, but it's like intrinsic to A, right? You find the eigenvalues of A transpose, and the non-zero ones are just the number of non-zero singular values. So you don't need to choose when to truncate it. It's just like, you can just stop it whenever you get to 0 or something. You just, so yeah, so maybe we'll do an example. So because you basically solve the eigenvalues of A transpose, you get all of these singular values, and then for each non-zero singular value, you're going to get a left and right singular vector. So these are called left singular vectors, the columns in here. And these are called right singular vectors. And so for each singular value, you're going to get each non-zero singular value, you're going to get a left and right singular vector. And then you just do that until you get to the 0, and then you stop. And that's the truncated SVD. And then for full SVD, you kind of, sometimes you'll have some zeros. You know, you might have, sigma might be something like, yeah, you might have 0 singular values, in which case you have to figure out your left and right singular vectors differently. So you might have something like sigma 1 through sigma r, and then some zeros, and that, like, this is all diagonal, and then you have a bunch of zeros. So some of these could be 0, in which case you can't solve for the singular vectors immediately. For the truncated, yeah, I believe so. If your singular values are 0, you can just truncate. You can stop it at your sigma 1 through sigma r, and then just stop solving for u and v after those are for the truncated. So maybe we can do an example. What example do we want to do? A is, coming up with examples for SVD is a little tricky because I never know how bad the calculations are going to be. So does someone have one from the homework maybe that they would like to go over? Or just not even if you like to go over, just one that you can provide. Otherwise, I might just put some random numbers in here. Maybe I'll look up. Okay, let's do 3. Okay, that's exactly the one I was going to do. This seems to be a common one. 2, 3, -2. Yeah, so for the truncated version, you're only going to get a basis for the column space and row space. Since you've truncated, you're not going to find bases for the orthogonal complements of those spaces. And so I guess that would be a reason to use full if you want a basis for the orthogonal complements. You know. Okay, so let's do A transpose. Does this change which vectors you can input and output for each version? I'm not sure what you mean by that exactly. Basically, for truncated SVD, you're finding a basis of column space of A and row space of A simultaneously, and then writing the matrix A in those bases. For the full, you're finding bases for the full column space and its orthogonal complement, as well as row space and its orthogonal complement. What would be any advantage of full? Well, okay, so the truncated, I mean, you're right. Like the truncated version seems to be like what in practice what you use mostly, because you're really only caring about like the whole point of SVD is to like reduce the amount of information you have. So truncated seems useful, but sometimes you do want to explain the whole linear transformation. So I mean, there's a linear transformation associated to A, and it goes from you know, some Rn to Rm. This is a linear transformation. And what the truncated does is that instead of looking at the full Rn to Rm, you would reduce this. So inside here are two spaces. The column space and the row space. Right, and so if you just kind of reduce your attention to the row space and look at TA just on the row space and what it does to the column space, then what you're doing is you're doing truncated SVD. You're finding bases of each one of these spaces and writing this matrix or this linear transformation in those bases. So truncated is you look at TA kind of restricted to the row space. And this is kind of a new, this is maybe a different, I mean, it's the same linear transformation, but like it's going from kind of a different space, row A. So the dimensions of the matrix associated to this will be different than A because it'll be going from smaller spaces. And the full one, you're looking at the whole thing. TA going from Rn to Rm, and you're finding bases of each space. Yeah, so then we wouldn't be able to input anything outside of row. Yeah, I guess if you're thinking about So, I mean, I guess the question is, what is outside of row A, right? Rn is what is outside, quote, outside of row A? What's left from Rn, right? So this Rn splits up into row space of A plus, exactly, that it's its orthogonal complement, right? The things outside of row A are its orthogonal complement, null A. And so by saying, really, I guess the better thing, instead of not being able to input anything outside of A, is that everything outside of A is just mapped to 0. Because that's what the null A is. And so if you were to input something, outside of A, like in the null space of A, it should just be mapped to 0. So that's why you're kind of just like forgetting that. Hence those zeros. Yeah, I see. Yeah. And this is column space of A plus its orthogonal complement. And so kind of you're including these things inside the full SVD, whereas the truncated you're just doing from row space to column space. Okay, so let's go back to the example, and maybe we can see exactly what's going on. So there's a question earlier, why did we use A transpose and not A transpose A? I did that because it's easier to multiply A transpose. You could do either one though, because if I did A transpose A, this would be a 3 by 3 matrix. And A transpose is a 2 by 2 matrix, and so it's easier to find the eigenvalues of a 2 by 2. That's why I chose this. But maybe we can do this one as well, and we'll see there's no difference. So what do we get? 9 plus 4 plus 4, 17. And then 6 plus 12 minus 4 is 8. And then 17. Okay, and so the eigenvalues, let's see, determinant of oh boy, okay, 6 minus okay, I don't know. Does someone want to quickly do this? 17 squared minus 64, 225. Oh, is that just 15 squared? Okay, great. That's a right triangle. Perfect. $25 and 9. Okay, great. That would be very useful. Okay. Lambda equals, so dot, 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 lambda equals 25 and 9. Use a computer, use a calculator, I'll help you there. Okay. And so the eigenvectors are 1 and 1 and 1 and negative 1. Okay, so I'm going to go to the next page. So you get 1, 1, 1, negative 1. You'll notice these are orthogonal, as they should be, because this is A transpose is a symmetric matrix. So we found, so I'll just rewrite what A is. A was 3, 2, 2. We found that the singular values are 5 and 3. The singular vectors, so we found are 1, 1 and 1, negative 1. We should figure out if these are right or left singular vectors. And we should also normalize these. So each one of these are eigenvalues of A transpose, or their squares are. And A equals U sigma V transpose, so A transpose equals so these should be the U's. So the left singular vectors. Okay, and we should normalize them. So so U1 equals 1, 1 for root 2. U2 equals, or I'll just, okay, now we need to find the right singular vectors. And so that's V1 and V2. Then what's the formula for that? And then maybe while we're doing this, or actually I'll do that later. Okay, so looking at this formula, we know what U is. So I think V1 should be A transpose U1 over sigma 1. Should be A transpose U2 over sigma 2. So I'm kind of doing the reverse again, maybe of what we learned in lecture, where I looked at A transpose instead of A transpose A. Either one will work. Okay, so what do we get? Over 5, 1, 1, 0. Right, the reason I got this formula, by the way, is if I multiply by V, or by U transpose on the right, because we're solving for V, then I get sigma V transpose, because we know what U is, we're solving, we want to know what V is. And so then I get that A transpose U equals V sigma transpose. And so this tells me what V, this tells me how to find V. If I multiply it by sigma, I should get A transpose U. Okay, so now I get 1, -1, 4 over 3. Is this right? Okay. And then, so what we're saying is that is that these vectors over here are a basis for the column space of A. So is that true? Yeah, that should be true, right? I mean, it doesn't look like that, but you know, not only that, there are orthogonal bases. Yeah, and then sigma equals 5, 3. I'll do the, let's do, and V is 1, 1, 0, 1 minus 1, 4. We should normalize these. Right, oh, I forgot to divide by root 2 everywhere. Root 2. So let me erase that. Because you want you to have a root 2 everywhere. Okay, and what we're saying is that these over here are a basis for row A, an orthogonal basis. Okay. And this would be truncated SVD. If we did full SVD, then we would want to expand these bases to bases for the whole space. So this matrix, you have, this is associated to a linear transformation. I'll write it a little lower. From what space to what space? TA goes from R3 to R2. So the column space is inside R2. So here's the column space. This is inside R2. And it actually makes up the whole space. So the orthogonal complement of column space of A is nothing. There's no extra thing we need to add. But here, this is an orthogonal spaces for the row space of A living inside R3. And there's actually some stuff left over. This doesn't make up, this is not a basis for all of R3. There's actually an orthogonal complement, a non-zero orthogonal complement to this row space. And if we were to include that, that would be full SVD. So if we were to include this, this vector here, call it a V3, this would be a basis, an orthogonal basis. I mean, it's only one vector, so it's automatically orthogonal. Orthogonal basis of null space of A. That's the orthogonal complement of the row space. And then we'd add one more vector here. We would add 0, 0. Right? Because then what happens when we multiply this all out? These zeros don't affect, because you put zeros here, none of this V3 is going to change any computation you did before. And so it's almost like it's not actually affecting, like you can write, A equals U sigma V transpose, but these zeros in this V3 doesn't actually like do anything because you're just being multiplied by 0. And just because the null space is just being mapped to 0. So what's in purple is the full SVD. So full SVD, you need to find V3. Truncated is everything in black. And maybe conceptually what we're doing is just adding a different base, adding more, expanding row space and column space to be bases of the whole space if they don't make up already the whole space. Okay, so just a quick question is how do we find V3? Well, we're just finding a basis for a null space, right? It needs to be orthogonal, and not only that, not only does it need to be a basis for a null space, but it actually needs, we want this whole thing to be an orthogonal basis for R3. So if we combine them all, this should be an orthogonal basis for R3. And so, you can set up the equation you need to solve by setting V3 to be orthogonal to these two vectors. So you form a matrix where these two vectors are the rows, and you multiply it by V3, and that should be 0, and that lets you solve for V3. So for the truncated, if you did A transpose A, yeah, so what if we did the other way, A transpose A? and you get a 3 by 3 matrix with one of your singular values as 0, do we just ignore the 0 singular value? Good question. I mean, I guess I don't really know if there's a well-defined notion, or maybe there is, but like a well-defined notion of truncated SVD. Like, when do you truncate, I guess, is the question. And my impression is that you truncate to only include the non-zero singular values. If that was done differently in lecture, you should maybe let me know so I don't spew false information. But my impression is that for truncated SVD, regardless of whether you look at A transpose A or A transpose, typically you just truncate to the non-zero singular values, and whatever those are the ones you keep. And then those are the singular vectors you solve for, and so forth. Yeah, so I think for if we went back and looked at A transpose A instead, then what we would find are the eigenvalues. The eigenvalues, I think, should be 25, 9, and 0. And so you just keep 25 and 9 as your singular vectors. So you get 5 and 3 here. Yeah. So are there any questions on what we've done so far? Right. So for the truncated version, U and V are not orthogonal matrices because they may not be square, for example. So right, the V we found, so the U we found was square just because the column space of A happened to be a basis for, that just happened to equal R2. There was no orthogonal or complement. But for V, there was a missing part of R3 from the row space. There was a non-zero null space. And so V is not 3 by 3, it's 3 by 2. So V, for the truncated version, is not an orthogonal matrix. But correct, V transpose V is still the identity because each column here is still, that the columns are still orthonormal. So in general, for truncated SVD, the matrices U and V are not necessarily orthogonal because they may not be square. But they do still have orthonormal columns. They should still have orthonormal. So you should still have the identities. Yeah, and so truncated SVD is typically more useful, I think, because in practice, what you really care about are these singular values. So you can kind of imagine like this sigma or this A being like a really big matrix. But then sigma, when you solve for it, is actually, I mean, it's the same dimensions as A if you did full, but imagine it had a bunch of zeros everywhere so that you only had very few singular vectors. Then what you could do is you could take all of your data points, which live inside some big Rn, and you could project it onto the space spanned by your singular vectors for the non-zero singular values, and that would be a much smaller dimensional space. And that's kind of the point of SVD, is that you can reduce some big matrix to like a very small matrix by just ignoring the components corresponding to 0 singular values. What is the geometric meaning behind V transpose V equals identity? Well, the algebraic meaning is that the columns are orthonormal. The geometric meaning would mean, I guess you'd want something like, what does it mean for the columns to be orthonormal geometrically? And that means that your linear transformation, by geometrically, I assume you mean like, what does it mean as a linear transformation? And that means that the linear transformation is either a rotation or a reflection. Geometrically, if V has columns, then, well, see, if it's V is square, I'll see, let me do this first, and V square, so that it's orthogonal. Then the linear transformation given by V is just a rotation or reflection. And that's kind of just because if V has orthonormal columns, then you have these two nice properties. One is that Vx, the norm of Vx, equals the norm of x. So this is a V square, I guess, because otherwise this doesn't make sense. And you have that the Vx dot Vy, so that the norms are the same and the angles are preserved. So that means this essentially means it's either rotation or reflection. And I guess if V is not square, then this would just be, well, the same thing. This would still hold. These would still hold, right? And so I guess you still have these two properties. Yeah, so that, I mean, that's kind of what it means geometrically, I guess. Well, I'll just leave it there. Okay, why don't we maybe take a short break and then briefly talk about differential equations for like 10 minutes or so. And then we'll talk about differential equations more on Friday as well. Okay. There wasn't much we went over in lecture, I believe, on differential equations. But there is a good review we should do while we have the chance, which is how to solve first order separable differential equations. This will come in handy just to know how to solve these. Maybe you went over this in like a calc class. So by first order, what this means is that only one derivative, or the highest derivative is 1, I'll say. We're also going to be doing just ordinary differential equations, no partial differentials. There's no more than one variable, it's just a single variable. And the highest derivative is 1. And separable means that you can essentially solve, you can put all your y variables on one side and your x variables on the other, just like you would solve a normal like algebraic equation. So for example, let's do y prime minus 3y equals 0. All right, so if you prefer, you can write this as dy dt or dx minus 3y equals 0. So this is separable because we can put all the y variables on one side and all the dt's on the other. So for example, here, we can write this as dy. So I'll do something that like most mathematicians hate, which is treating this dy dt as like as not like an object, but as separate dy's and dt's, which is kind of scary to do. I'm gonna put this in quotes because this is really a function, and it kind of doesn't really make sense to do this. But for some reason, we teach it this way. Or over here, you can just do y prime over y equals 3 if you want. Is maybe better. And then you just integrate, right? Now that the t's are over here and the y's over here, this is what I mean by separable. And now you can integrate. And so this is an equation you're gonna very familiar with. Right, this is log y. A plus a constant. So y is equal to some a e to the 3t. Right, so this has solution. General solution is y equals a e to the 3t. So we're going to get very familiar with these exponential solutions to these equations. Okay. Maybe something that's not separable. What if we have, for example, two differential equations, or a second order differential equation, I mean? That would be not separable. So for example, something like a y double prime plus b y prime plus c y equals 0. I mean, first of all, there's a second order here. So we can't really do the same tactics we had before. But we're going to find ways to solve this. In fact, we probably already went over one in lecture. So just a little theory first, and then how to actually solve it. Right, so slash just connection to linear algebra. We can view this ddt as a linear operator, linear transformation. We kind of talked about this a little before. We had linear transformations from polynomials to polynomials, and we had this derivative function. So we've dealt with some examples of this where this is a linear transformation. But now it's going from the vector space of, well, it's taking in these functions of functions, say from R to R, back to V. So it's, and sometimes we put some quantifiers on these functions, So we can say continuous functions or smooth functions or differentiable functions. I guess we haven't really defined what smooth is. Differentiable. So other quantifiers you can use for these functions. But the point is, this is now a linear transformation, not from polynomials or column vectors, but from this big vector space of functions. And this is actually what's called an infinite dimensional vector space. But we can still use these properties of linear algebra. So we can view differential equation A, so this is called as star, as a linear equation, as the linear equation dy equals 0, where d is a linear transformation from v to v defined by a y double prime plus b y, or I'll say a d squared by dt squared plus b d by dt plus c. So in other words, d takes a function and it outputs second derivative times a plus first derivative times b plus f times c. And so this differential equation is just a linear equation. And the point is, finding solutions of star is equivalent to finding vectors in the null space of D. The kernel of D. Right? And this is something we've talked about like for the almost all of the semesters. How do you find a basis for a kernel or a null space? Right? So this is exactly what we're doing. When we're solving differential equations, we're trying to find a certain basis of the kernel. Except now the only kind of tricky thing is that this D is going from a vector space that's infinite dimensional instead of some Rn. So it's a little more confusing maybe, but the principle is still the same. We're just trying to find vectors in the kernel of D. Right, and so now, sorry, this is the last page. How to actually solve this differential equation. Basically, I'll do this fast and then we'll go over it on Friday. So that basically how you solve all differential equations is you guess a solution and then you check your solution and you figure out what it has to be. This is like mostly how differential equations are solved in my opinion. So a good guess that we're going to figure out is that y is some e to some kt for some k. And then you figure out what it has to be. So if you plug that in, you get a times k squared e to the kt plus b k e to the kt plus c equals 0. I'm plugging in y for everywhere I see this. There should be a y here. I think I put, hopefully, yeah. Equals 0. And so then you have this equation, and that lets you solve this quadratic. Okay, my K's don't look that good. Right, and so solutions to this quadratic give you K. And we'll talk about more solutions on Friday. For example, what happens when, so if you have two distinct roots to this quadratic, then you get two distinct polynomials that are solutions, or not polynomial, two distinct functions that are solutions to this differential equation. If they're not distinct, then what do you do? If they're complex, then what do you do? And so more on this on Friday. And I'll end there. So I'll be on for a little longer if you want to ask questions in general for class or for the exam.